Okay class. So class, today we will find out moment of inertia of thin rod. Okay, we are to focus on keywords, and here the keywords are moment of inertia. One is moment of inertia. It depends upon mass distribution. First factor you are to keep in mind is mass distribution, and another is the axis about which you are finding the moment of inertia. And then you have thin rod. It means rod. From here you can take idea that the mass distribution will be linear mass distribution. Here the mass distribution is linear mass distribution. Okay, so let us assume that this is the axis of rotation which is passing through center of mass of a rod, and this is the rod. Okay, and the length of rod is, let this is capital L. Okay, or you can take it 2L. Let this is 2L. Okay, and the mass, total mass of this rod is capital M. Total mass is capital M. I have told you this is the case of linear mass distribution. So if you find the linear mass density that is lambda m, this will be total mass of the rod divided by total length. Okay, so this is the linear mass density. Now what you will do, you will divide this rod into elementary length elements of length dl. Okay, and suppose this is at a distance of small l from the axis of rotation. This is this is z axis. It is passing through center of mass of the rod and perpendicular to its length. Then the moment of inertia, I am writing in short, moment of inertia of elementary length element of length dl and mass dm, it will be, let we represent it by di, and it will be dm into l square. You see, the mass of this element is dm, okay, and its distance from the axis of rotation, that is small l. Okay, now you are to find this mass of this length element. It will be equal to the linear mass density lambda m into length of this length element, that is dl. Okay, so if you substitute its value, then you will get lambda m into, I am writing l square, and lambda m into dl. So this is the moment of inertia of this length element which is at a distance of small l from the axis of rotation. Okay, now to obtain the moment of inertia about this axis which is passing through center of mass, then what you will do, you see, to cover this complete rod, you have to move this length element from this side to this side. Okay, and when you start, suppose from this end and come to here, you will see the length will decrease, and after this it will increase. So our limits of integration will be from minus L to plus L. Okay, so the moment of inertia of complete rod can be obtained by integrating di within limit minus L to plus L. Okay, and here you see this is constant because you are assuming that the linear mass density is constant or mass distribution is uniform. So you can take this factor out of integration. Okay, then you have L square into dl, and our limits of integration are from minus L to plus L. Okay, if we substitute the value of lambda m, this is m by 2L. Okay, then integration of L square will be L cube by 3, and if you substitute its limit minus L to plus L, then you will get the result. Okay, so from here you will get, let me solve it, it will be m by 2L into, this will be 2 by 3 of L cube. I think this will be the result. Okay, so 2 will cancel here, and then you will get L will also cancel, and you will get L square. So this will be m L square by 3. So this will be the moment of inertia of the thin rod about an axis which is passing through center of mass. Okay, now suppose we have another axis which is passing through the end and one of the end of the rod, and this axis is perpendicular to the length of the rod. Then let this axis is AB, and to find the moment of inertia, what you will do? You will make use of parallel axis theorem. Using parallel axis theorem, the moment of inertia about axis AB, which is parallel to z axis, and it is passing through the center of mass, and this axis is at a distance of L, you can see. Okay, and the mass of rod is capital M. So it will be IZ plus mass of the rod and distance, square of the distance, that is L square. So if you substitute the value of IZ here, IZ is ML square by 3 plus ML square, so it will give you 4 by 3 ML square. Getting it? Now you can think of the moment of inertia. Now you are to focus that the rod is thin. This rod is thin. So this thickness here we have taken negligible. We are neglecting it because this is very thin. Okay, why I am telling this? Because if you take any axis which is along the length axis and passing through center of mass, in that case this distance will be negligible. So the moment of inertia of such a rod which is infinitely thin, you can say, because we have taken here the linear mass distribution, then the moment of inertia about this axis will be negligible, and it will be about approximately equal to 0. Okay class, so these are the cases. In case of thin rod, you can take the axis anywhere. Okay, anywhere. Let this is at a distance of x from here, and this axis is let a dash b dash. Then also you can find out moment of inertia about axis a dash b dash using parallel axis theorem. In that case, this distance will be x instead of capital L. Okay, so the moment of inertia about a dash b dash, this will be the moment of inertia about z axis plus the moment of inertia plus the total mass, product of total mass of the rod and this distance, that is x square of this distance, x square. So class, this is how you can find moment of inertia of a thin rod. Thanks for watching the lecture. गड़बड़ होगी कैसे? Okay class, in in some of books you will find that the length of the rod is taken L. So in that case the limits of integration will change from minus L by 2 to plus L by 2. Okay, and the whole results will change, and here you will get L by 4 instead of L, and your result will become M L square by 12. Okay, so don't get confused. You have to keep in mind that what is the length. The result may differ depending upon the length you have taken.